Look up on a clear afternoon, and the zenith is a crisp blue. Wait a few hours, and the horizon bleeds into a deep red. Introduce a wildfire, and the air turns a milky, suffocating amber. Toward the poles at night, the sky glows a vivid green. We perceive these four skies as entirely distinct physical states, yet the light leaving the sun is uniform, broad-spectrum white light. The gauntlet begins the moment that white solar beam impacts the upper atmosphere. A single mathematical ratio, the size parameter, dictates the resulting color, defining the boundary between light that is scattered and light that is actively emitted. To look at the sky is to observe a massive, real-time mathematical equation measuring the physical dimensions of invisible particles. Tracking the solar beam into the atmosphere reveals immediate collisions with trillions of diatomic nitrogen and oxygen gas molecules. The light wave acts as an oscillating electric field. As it hits a molecule, it displaces the electron cloud, turning the gas molecule into a tiny dipole antenna that re-radiates energy in all directions. This is elastic scattering. The size parameter equation determines the strength of this interaction by comparing the particle's radius to the light's wavelength. Atmospheric gas molecules are significantly smaller than visible light wavelengths. The resulting size parameter is less than 0.1, entering the Rayleigh scattering regime. Lord Rayleigh derived that in this regime, scattering intensity is inversely proportional to the fourth power of the wavelength. This exponential relationship means shorter wavelengths like violet and blue are scattered up to 9.4 times more aggressively than red light. The clear daytime sky acts as a planetary scale disperser, actively stripping these shortwave colors out of the sun's direct beam and scattering them into our line of sight from every direction. Rayleigh's inverse fourth power law suggests that because violet light has the shortest wavelength, the sky should appear deeply violet. The first mechanism preventing a violet sky is the sun's own black body emission spectrum. The sun physically produces significantly less violet light than blue. The energy drops off sharply at the extreme left edge of the visible spectrum. Human biology provides the final filter. Our trichromatic vision relies on three distinct types of retinal cones. The human visual system is optimized to detect blue light, but possesses poor sensitivity to violet wavelengths. The peak of the scattered solar radiation aligns almost exactly with the peak sensitivity of our blue cones. Sky blue is a biological translation of scattered radiation, a specific perception mediated by primate evolution. At sunset, the geometric path of light through the atmosphere lengthens, a metric known as air mass. Light reaching an observer at sunset travels through up to 38 times more atmosphere than light at solar noon. The Beer-Lambert-Bouguer law dictates that as this optical depth increases, the transmission of shortwave light decreases exponentially. The blue and violet photons are scattered away long before the beam reaches the observer. Empirical spectrometer data taken over the course of an afternoon confirms this depletion. As the timestamp approaches 1800, the blue and violet lines experience a severe downward plunge. The shortwave light is being removed from the direct solar beam. The longer end of the electromagnetic spectrum shows the inverse reaction. Right as the blue light vanishes, the red and orange data lines experience a massive spike. A red sunset represents the visual leftovers of a solar beam that has had its blue and violet light amputated to create a daytime sky somewhere else. Increasing the particle radius in the size parameter equation shifts the optical behavior of the atmosphere. When atmospheric particles like water droplets, dust, or smoke are comparable to the wavelength of light, we enter the Mie scattering regime. Mie scattering is largely independent of wavelength. Instead of dispersing light uniformly, these larger particles throw light forward in a concentrated antenna-like lobe. In wildfire smoke, high concentrations of organic tar balls act as a massive bandpass filter, absorbing blue light and creating a hazy, orange-saturated sky. This regime defines the permanent state of the Martian sky, where the atmosphere is continuously choked with iron-rich dust. A planet's baseline sky color depends on the specific physical radius of its most abundant suspended particles. The night sky operates differently, shifting from filtering solar photons to actively generating its own light. This marks the physical boundary between elastic scattering and quantum atomic emission. Highly energetic charged electrons from the solar wind are funneled by Earth's magnetic field into the upper atmosphere. As these electrons collide with oxygen and nitrogen ions, they transfer their kinetic energy, forcing atmospheric electrons into unstable, excited states. These excited electrons immediately relax back to their ground state, releasing a brand new photon of a specific wavelength, such as auroral green. Auroras represent a planetary-scale neon tube, a mechanism fundamentally distinct from the scattering that defines the daytime sky. These incoming solar photons face a continuous gauntlet. The Rayleigh regime selectively strips away short wavelengths to produce our blue midday and red sunsets. The Mie regime involves larger aerosols like smoke and dust, creating wavelength-independent hazes and alien skies. Atomic emission allows the atmosphere to bypass scattering rules, generating its own light through quantum relaxation. Ultimately, looking up at the clear sky reveals a continuous collision of quantum mechanics, particle physics, and human biology.